semantics work on Verilog. And due to the time constraints, I won't delve into the details of Verilog and the semantics. So don't worry, you could easily understand my talk. I will firstly introduce what is Verilog, and then give a motivation example to explain why we need the Verilog semantics work at this point. Then I will give a brief introduction to Lambda V, the core language we present in this work. And finally, I will show usefulness of Lambda V. Verilog is the most popular hardware description language which is used to define hardware. So let's compare it with software languages like C and Java. While C and Java programs can be compiled into executables, Verilog programs can be synthesized into circuit-like representation. Oops, sorry. Yeah. And yes, the Lambda V programs can be synthesized into circuit-like representation, which can be further manufactured into the real circuits, like the chips in your mobile phone or laptop. So when we develop software, we need to test them by running executables on various test cases. But such tests cannot be performed on the real circuit to test real circuits because producing real circuits can be very expensive. So instead, to ensure the correctness of hardware designs, we usually test Verilog programs by simulation, which is similar to interpreting like a Java program. Verilog is already a mature language. So why we need a semantics work at this point? Well, there are several reasons. Today, in the field of hardware design, we are witnessing a shift from general-purpose processor to domain-specific architectures, which is largely driven by the proliferation of AI techniques. And such a new trend raises new challenges in productivity, reliability, and security in hardware development. At the meantime, Verilog is an important infrastructure in hardware design. New languages like Chisel use Verilog as backend because Verilog has industrial strength support for simulation and synthesis. And also, many existing hardware security and reliability techniques are built for Verilog. However, Verilog is designed by hardware guys. They don't really know PL. So Verilog has a number of semantic pitfalls which confuse hardware developers and language tool developers, which further lead to bugs. Let's take a look at a simple example. So this is a Verilog program, and you don't need to understand every detail. I will explain the key parts. So Verilog uses modules to organize and reuse code. And then here there are some data declarations, which is very similar to variable declarations in software language. So here we define 4 variables. They are all 1-bit values. At the bottom, we want to connect variables A and B by an AND gate. In Verilog, there are 2 ways to do this, which are usually considered equivalent. The first way is to use continuous assignment. It's a unique feature of Verilog. So when we write a code like this, then whenever A or B's value changes, the A and B, this expression will be recomputed, and the result will be used to update C2. And the second way to do this is to use always block like this. So we write some expressions following keyword always. And these expressions can be seen as trigger events. For example, post edge A means that A's value changes from 0 to 1. And next edge A means that A's value changes from 1 to 0. And the same goes for B. So basically, we enumerate all possible value changes of A and B. So whenever these events are triggered, then A and B will be recomputed, and the result will be used to update C1. So since that these 2 ways it seems that they are equivalent, right? So to confirm this, we write test bench to check the equivalence of these two ways. So if C1 is equals to C2, then the program will display same. Otherwise, it displays different. And we run this program by Icaros Verilog, which is virtually the most comprehensive open source Verilog simulator. And its result is surprisingly different. So if I were a hardware developer, I will feel confused. And you might think, is this a bug in the simulator? Well, to answer this question, we need to check the Verilog standard. And according to the standard, for this program, both same and different are possible outputs. So if I were a language 2 developer, I will also feel very confused. And finally, we found that actually it is a semantic pitfall in Verilog. And it is not the only one. After careful study of the Verilog standard, we found and summarized a series of semantic pitfalls and summarized them explain them in this table. For example, this row explains the pitfall we just solved. So to clarify these pitfalls, we need a core language with formal semantics. So we introduce lambda v, which is a core language, and it can be distinguished from Verilog programs. Lambda v has some favorable features. And first, it offers tractability as a core language. And Verilog is a very complicated language. So we need to carefully design lambda v to keep it as simple as possible. So here I just showed its syntax, runtime states, and transition rules. So it is fairly simple compared to the Verilog. And second, lambda v provides so far the most complete Verilog semantics. And we have implemented a compiler and a simulator for lambda v, which contains 27,000 lines of code. And here is an example. So the left side is the Verilog program we just saw. And our compiler will distinguish such program into a lambda v representation like this. So let's have a quick look at their corresponding parts. And the tool can be found in our artifacts. And finally, lambda v is well tested to demonstrate the totality and conformance. I will explain this later. And these good features of lambda v can enable us to do some useful things. For example, it helps us to detect 3 categories of semantic bugs in open source simulators, and expose 4 types of ambiguities in Verilog specification. Also, it can facilitate language 2 development, such as concolic execution. And I will explain the 3 points. Lambda v is not the only one semantics work for Verilog, but it is the most complete one. We compare lambda v with other semantics works for Verilog, and here we summarize the results. So basically, each column represents a Verilog feature, or a category of Verilog features. And we use different circles to represent different levels of support for Verilog features. So we can see lambda v is much more complete than all other semantics works, including the state of art. So basically, lambda v can fully support almost all Verilog features, except these 2, LT and STF. But LT is rarely used, and STF is like a library functions in software, so it is unnecessary to model all of them. And to be useful, lambda v should have 2 important properties. Totality, it means that we can distribute all Verilog programs into lambda v. And conformance, it means that the distributed programs should generate the same results as the original one. And to thoroughly validate these 2 properties, we test lambda v using such strategies. So first, given a Verilog program, we distribute it to a lambda v program. Then we run simulation on both programs and then compare their results. We use 2 comprehensive test suites. The first one comes from Icarus at Verilog, which is the most popular open source Verilog simulator that I mentioned before. And it has more than 800 test cases covering various Verilog features, so as shown in this table. So each feature is counted once if a test case uses it. So it is a thorough test suite. And the second one comes from open source projects like OpenPitot and Altera. And these Verilog programs are non-trivial, ranging from 100 to 1,500 lines of code. For example, it includes an implementation of a RISC-V CPU. So what is the testing result? We found that LambdaV can pass almost all of these cases, except several ones. And some cases are incorrectly written by the developers. And other cases cannot pass LambdaV's stricter type checker, because Verilog allows implicit type conversions, and LambdaV is designed to reject such cases because we found that they often lead to bugs. So overall, LambdaV demonstrates the totality and conformance to accommodate the various language features and real-world programs. I will use a case study to show the usefulness of LambdaV. And we ask an undergraduate student who knows something about concolic execution but is totally not familiar with Verilog. But with LambdaV, it took him about 100 hours to implement a concolic execution tool, which works well on a popular benchmark called ITC99. And this benchmark is widely used, and it consists of real-world programs. And the concolic execution tool written by the undergraduate students exhibits decent results in terms of branch coverage and performance. So to conclude, the new trend in the hardware development raises new challenges in productivity, reliability, and security. So to tackle these challenges, in this work, we propose LambdaV, an operational semantics for Verilog, which is tractable and well-tested. It can help clarify the pitfalls in Verilog and facilitate building language tools for Verilog, such as concolic execution tools. We expect that LambdaV to be useful for more potential applications. So ultimately, we hope that we can bring the successful principles and experience in the software community into hardware development. And if you are interested in the semantics, and please refer to our paper. Thank you.
Please step up to the microphone to ask a question.
Thanks for the talk. I'm glad to see you have some user study that asks if an undergraduate student can use this software semantics to understand the hardware language. But on the other side, I heard from many hardware people that when you learn hardware language, you shouldn't use software thinking because it's wrong. You should use hardware thinking so that you can really understand the real semantics of their language. So I'm wondering, is it possible that, or maybe you have ever considered that maybe you can ask some hardware people to read this kind of formal semantics, or maybe you can explain that to them in some more intuitive way so that they can agree that yes, this is consistent with what the so-called hardware thinking.
Well, we will definitely do this in the future, but indeed there are huge difference between the hardware language and software language. But I think in software language we have many successful experience, I think, which are definitely useful for building hardware. Especially the experience that we use to manage very huge software projects. And nowadays, the hardware also become more and more complicated. So maybe a powerful CPU, its implementation may contain many lines of Verilog code. So we think we can definitely help to improve their productivity.
Yeah, I agree, because nowadays they also use like software-defined hardware, for example. So I
Yeah.
believe this should be possible, but maybe we should investigate this problem further to, to really convince those hardware people that you can have some formal model to explain what their languages are actually doing. Thanks for your honors.
Yeah, thank you.
You mentioned you have a two feature you do not cover. Are you choose to cover in the future work, or you purposely leave them out in the semantics?
Well, let me see. Let me show these two.
I think it's FT and
Yeah. Yeah, maybe not, because, but it depends. So LT is rarely used, and also it is not synthesizable. So this feature is not commonly used in Verilog, but it is.
What is the usual use case in this particular LT? How hardware people normally use them?
Usually, usually you use this tool in an extension of Verilog called System Verilog.
Oh, I see. So you choose to ignore this. You choose to not cover feature in the System Verilog.
Yeah, currently not.
Okay, cool. Sorry, I'm from industry. I'm from ARM basically, but from what I heard, most hardware company they use System Verilog very consistently because it's more useful for engineer to use System Verilog. But potentially that is one of the feature people using. So that's why I'm asking the question.
Okay, I see. Thank you.
I have a quick question. So what kind of, so you have a mechanized semantics, right? So you actually tested it against all these tests. So how did you actually implement the semantics? And did you also think about like formalizing it in a way that you can do proofs and prove some properties about the semantics?
We do this by testing, because we think even we can formally prove some like properties, but if our implementation has some bugs or has some problem, we cannot say our tooling or our tool chain is useful.
All right. Thank you very much.
Okay,
Thank you, speaker.